Okay, well, I'm not going to talk about the level set method, which is more appropriate for this meeting. However, I do believe that this stuff I'm going to discuss will have applications in mixing and interfaces and whatnot. It's towards large scientific learning models. It's joint work with three postdocs who are really good, mostly Liu Yang. The idea is in context operated learning with data prompts for differential equation problems. This appeared in PNAS about a week ago, 2 weeks ago. Next slide. Oops. Okay, so what am I doing? Neural network-based models for solving differential equations are very popular. You all know about PINs probably, and there's FNO and depot nets, but they are limited by equation specificity. You need frequent retraining when switching to new problems. So what we're going to do is use ChatGPT, would you believe, or something like it, large language models, to solve PDEs and, in fact, scientific problems in general. We call it in-context operated networks, ICON, to use a single neural network to solve a wide range of scientific machine learning problem tasks. No retraining, no fine-tuning in the neural network. You leverage commonalities across various tasks. So only a few examples are needed when learning a new operator. Of course, there's a lot of training, but the idea is to develop models that can adapt to new physical systems and tasks like a human would. Let's talk about it next, please. Okay, so what is this about? Let me see, this is blocking my slide. You're operating, I can't see this stupid thing. Okay. You operate from left to right, okay. You have quantities of interest, pairs associated with a bunch of unknown operators. ICON is trained to be an operator learner instead of an operator approximator. You prompted examples and the question condition. The model learns the operator from the examples and applies to the question conditions. Output prediction of the questions and quantity of interest function is queries, and there are no weight updates. So the idea is you input a ton of data, then you query against some new data and figure out what it's close to. Very simple idea. And there are no weights, and there's no changing things. If you change the problem, if you want to solve a differential equation, you do not have to, and you just change some parameters. You don't have to redo it, which is usually the case for the other methods. Moreover, the data we input in the numerical analysis situation is really solving differential equations using state-of-the-art methods of a certain, for a certain class of equations. For example, you pick a topic and you feed in a whole bunch of equations that come from that topic, feed in solutions using state-of-the-art numerical methods, if you have them, with fixed parameters, many fixed parameters, many different parameters. You store all this stuff and then input something else and find out what it's close to. So crudely speaking, it's like finishing sentences, just like natural language processing. And it seems to work. And one of the many advantages is that inverse problems are automatically, doable, because you're starting from, I'm talking about time-dependent evolution equations for the moment, which is appropriate for this conference. And you go from 0 to capital T, and you can see the results and perhaps solve inverse problems, which seem to work, and this seems to work. Another thing I will point out, I'm obsessed with discontinuities, and the other competing methods use automatic differentiation and whatnot, and they cannot deal with discontinuities or steep gradients. So at the end, I'm going to talk about solving shock problems, inverse problems for shocks, conservation laws. We're using this stuff. Okay, next. So this is what we started with. It's 19 different simple differential equations right now, but we can scale it up, and we're doing it. We start out with some ODEs, first order, second order. And the most complicated thing we're talking about is mean field control, which is an interesting problem. So that has space and time. Each of these problems includes forwards and inverse possibilities. PDs, mean field control, solved with a single neural network with about 30 million parameters. So what I really like about this is inverse problems just fall right out. And amazingly enough, they seem to work, even for example, inverse Burger's equation. Okay, next. So this is what icon does. You have a differential equation. And the important line is the solid black line, which tells you that the ground truth is right on top of the prediction for these problems. ODE3, whatever that is, I forgot. There's quantities of interest down below. And on the right, there is an inverse problem, which I really like, a reaction diffusion equation, a simple one. And we get good results for this 1D problem. Admittedly, it's only 1D, but we're getting there. Okay, next. This is in distribution operators. What we can do, we have a set of equations which have parameters, for example, A, B, C, and we can get an out of distribution. We'll do that later, our operator, which is more general. If we seek an out of distribution operator and we use these guys, we'll get something close, and we have found that we can actually compute new operators this way, under some circumstances. So the main takeaway here is that the relative errors are small for forward problems, bigger for inverse problems. But for example, in the center, we have this so-called Poisson equation, which is just UXX equals AUX or something plus forcing function. And we can recover the coefficients and essentially the boundary conditions. Okay. And mean field control, we get relative error of 0.01, 0.02, things like that, depending on the number of examples we test. And once you train this stuff, it's lightning fast. So it's very satisfying to try to figure out what a differential equation is, or better yet, how to solve, what the parameters are. When you input some, I think one of the parameters could be the solution, for example, or the solution to an inverse problem. After you finish inputting this huge amount of data, which doesn't take, I mean, not that huge by the standards of the subject, and you see some nice results coming out. Next. So this is a 2D problem. This is mean field control. You can see it up above. It's a mean field game of a simple sort, and you're optimizing something. 3 examples and the question share the same terminal cost as the unknown parameter in the equation, in the operator, sorry. And we're plotting a density field in space-time. And what we did is kind of cute here. The blue dots are the data for the example condition, the densities at time t from 0 to 0.5. And the red dots are what's predicted for the 0.05 to 1. In other words, all we're doing is solving the problem, inputting the data from 0 to capital 1 to 1/2, which is half the time step, half the time length. And then we're predicting the data from then on. And the results are good, as you can see. The prediction and the ground truth are down below, and they are pretty close, except at the boundary where you see some red stuff on the right. So this, we make the prediction on rho, solution to that differential equation. for t and go between 0.5 and 1 based on what started before, and not knowing what the equation is, although having done, again, one more time, having solved many, many equations with different parameters and input that stuff. Okay, next. Unsurprisingly, if you input more data points, you get better results. Same problem, mean field control with terminal cost as the unknown parameters. As you increase the number of data points in each condition, quantity of interest function, the error decreases and finally converges below 1%. And ICON uses 41 to 50 data points in each function represented by the narrow red region. So that strip in the middle is all we are inputting. And then we're going back and forward. I mean, this goes against everything I've done most of my life, not worrying about well-posedness or inverse problems or anything. And it's a little bit scary that it works. So we have to figure out why. And but right now it's very promising. Okay, next. This is out of distribution operators. So that the black curve, the black square gives the parameters for a differential equation, A1 and A2 and A3, or whatever they are. Okay. And what we're doing is solving this differential equation, just given these values of the parameters for input data. And you can get prediction even beyond that square, where you're out of distribution of what the A's can be. So you can extend beyond the training region, which is a little bit scary, but it seems to work. It's a simple problem, but we'll scale it up. Okay, next. You can get new forms of differential equation. I won't go through this complicated diagram, but the basic idea is you get a new you get a new differential equation, which is not in the training space by you find a different, you're looking for a differential equation of the type on the right using data for differential equations, for different differential equations, but related ones. And as the training data set becomes larger, of course, there's learning operators for equations that were never seen in the training data. Okay, next. And next, this is fun. Let's go back. Sorry. I didn't mean to say that next. The results came from a first paper where we used transformer-based encoder, but now a second paper, we're using a language model-like architecture where this thing talks to you, God help us. So you only have one transformer, it's a little simpler. There are fewer, so we made it better, fewer parameters with higher accuracy and multimodal. You take the captions as input that integrate, apart from the data, you also take in the captions that integrate human knowledge about the operator expressed through natural language descriptions and equations. Of course, you have a class of possible statements with missing data, which you input. So it helps. The in-context learning with data prompts for differential equations really give you more accuracy, incredibly enough, if you can deal with language, as well as essentially estimating differences of things or commonalities of stuff. Next. Okay, so for those of you who care, this is inspired by large language models. It uses the input condition quantity of interest pairs in autoregressive ways. Special attention mask is tailored for operator learning, which keeps variance for tokens of the same function. But anyway, so there's some clever computer science going on here. Okay, next. And the captions help. If you put a vague caption in, what these diagrams are telling you, that if you put in a vague caption, the results you get are not nearly as good as you put in a precise caption with numbers. And that's what those diagrams above are telling us. For what problem is this? This is for ODEs and forward damped oscillations. Okay. Next. Oh, this is my favorite part. Okay, so here we go. This hasn't been published yet or written up yet. We're going to take a baby problem, which I promise you will translate eventually into something more complicated. We're doing Euler's equation now in two space dimensions. Anyway, so this is generalization. This is conservation law with three unknown parameters: ut plus ddx of f of u. F is auq plus bu squared plus cu. Periodic boundary conditions, unknown parameters. We have a forward operator, and we have a backward operator. And the backward operator for a numerical, obviously for conservation law flowing forward is certainly not unique. However, we pick one out, which is fairly amazing. We pick one out which satisfies the entropy condition, has the right shock jumps, and does all that stuff. And we show that's true because after we've picked out this reverse thing, we go forward with a true solution operator, and we get the right answer. So the data is generated by solving the conservation laws numerically with third order we know, for those of you who know about this stuff, weighted essentially non-oscillatory schemes. You reduce computational costs during training, and you learn from, I like that language, battle-tested numerical schemes. And this, I want to stress, is something that the competition cannot do. As I said, they're all inputting differential operators and using automatic differentiation and no fancy finite difference schemes, and they cannot deal with discontinuities or steep gradients. If you see these guys solving Berger's equation, they kill it with viscosity. Or they do the same thing over and over again for Navier-Stokes or motion of vortices or something with lots of enough vorticity to take care of discontinuities. We do the real thing with good schemes, and we just match the results of our operators' solutions, which is easy to do once you have the code. Grind away, learn everything, input everything, and then turn the crank. Let's see what we get. Next. Okay, so you randomly sample A, B, and C. Then for each A, B, C, you sample from a periodic Gaussian process. You use third order Wiener finite volume. I like this language. And fourth order Runge-Kutta method to solve conservation law. We have small delta T over delta X, but we don't care. This is AI. This is fast like crazy. Consider every time step within the interval, some time interval. Treat it as individual initial condition. Each has an associated function that appears 0.1 time units later. They will form a condition quantity of interest pair for the forward-backward operator. And so this is how we prepare the data. Okay, next. And the results are right on the money. That is, what you see is the initial data, and then we see the solution at a later time, and the solution at a later time overlays the true solution with the forward prediction, and it's very, very close. For this crazy case where A equals B equals C is minus 0.6. So we have rarefactions, we have shocks, we have God knows what contacts, anything in this stuff. We don't care. We just solve it numerically for the scheme which we know converges. Well, with high order accuracy, including at discontinuity, close to discontinuity. And then we input new data and find out missing parameters, what the equation might be, or we find out how we solve it instantaneously if we have the initial data and the solution, or we solve an inverse problem, which I really love. Given data at for large T, we go backwards. Okay, next. Here's more examples with the different A's. But the moral of the story is, given initial data, which has all kinds of possible discontinuities, kinks, jumps, rarefactions for problems which are totally non-convex, which with conservation laws, which include very complicated solutions with rarefactions and so on. We get them all. And again, it's only 1D, one space dimension, but we get the right answers very accurately for this class of problems. We find out the coefficients. And again, it's only 1D, but more is happening. Scalar. Next. This is my favorite, backward operator. We have non-uniqueness of the backward operator. That is, we have solved, again, having input all the data, we know a whole bunch of backward solutions because we have seen the entire thing for the right answer. Then we take our backward data for the unknown equation and go backwards and do our number on this magic on this thing, and we get pretty good results. The lines are almost overlaying. And surprisingly, if you go backwards, you get something which is predicted as the initial data or earlier data. How do we know it's right? We go forward with an accurate scheme for a well-posed problem, and we get back what we started out with. So this really opens up a lot of possible ways of solving inverse problems without knowing anything, which really makes me nervous. I'd like to get some theory justifying this. But right now, it seems to be working. And this is my favorite set of examples. And again, we're solving differential equations with no worry about discontinuities because we have schemes that can handle them, as what we input. Okay, next. More examples with backward operators with various constants. And again, the moral of the story is that the solution and the predicted thing are pretty close. Not as close as for the forward operator, of course, but not bad. Okay, next. There's the relative error for backward and forward. And of course, backward is worse, but it's not terrible. And of course, if you have too few examples, it gets worse. With lots of examples, even backward's not bad. Okay. And again, the backward predictions are accurate. It's a low consistency error. Consistency means if you take the backward solution and grind out with the forward solution, you get what you know is correct. All the predictions, including forward and backward, are given by a single neural network. So after you've spent a day and a half or whatever inputting the data, then you turn the crank and get answers very quickly. Okay, next. How does this work? I don't know. This is a lot of words with no equations. In fact, this has fewer equations than any talk I've ever given. You need to learn the operator for a certain distribution of conditions. We leverage the commonalities. That's a funny way of saying that we're computing some distance between outputs in training and testing operators. ICON needs to identify the equation and the hidden parameters. For a larger family of operators, you require more examples, especially for complicated operators, and a larger neural network with more training costs. Okay, so what are we going to do next? It's easy to say this, but I think it's going to work. And next time I see you guys, I will be talking about, I promise, more complicated problems, hopefully things with interfaces. We want to scale up. Large language models improves generalization beyond human expectations. Now, that's a dangerous statement. But if you've played with ChatGPT, it's a little bit unsurprising. This is very much like choosing a next word in a sentence, given a whole bunch of sentences and similar topics. The numerical in the AI ecosystem, my students wrote that, my postdoc. Numerical tasks is a weak spot. We anticipate the possibility of AI for general numerical tasks with large ICON models. Next. And here is a pseudocode, which you can stare at. Okay, it was not very complicated. And next. But there is no next. Okay, I guess I'm finished.
We got time maybe for 1 or 2 questions.
So I'm not familiar with this field, but it seems like at least some of this could be done also with symbolic regression. Is that common, or has anyone tried that?
I don't think so. I mean, it's quite, you're talking about how to match or something, or how to do commonalities. There's optimization hidden in this. And it's very hard to get people to tell you what's exactly in these language models, to be honest. I have to, but in AI in general, optimization pops up all the time. So what you're talking about might be used. I'm not sure. Anything else?
The approach that you describe, how can it improve numerical modeling of interface dynamics and interfacial mixing?
Very simple. We use my fabulous level set method and do the same thing for problems with interfaces. Take a fluid flow with a whole bunch of bowls with different possible parameters, or solve Navier-Stokes equation with two-phase flow or something, and look for or do a gamma log gas and try to figure out what gamma is with interfaces, or solve Hamilton-Jacobi equations, which pop up in interface problems very quickly.
But this was not done yet, right?
God, no. So I'm sorry, I'm cheating. I'm talking about something which is not directly part of this conference, but I couldn't help myself. But I do believe that this will generalize very much, including the stuff that we should be talking about here, which interests me.
One more question. Yeah. Usually when we try to solve differential equations is to understand some physics. So I have some difficulty here to understand how that would be achieved if we just...
Well, I'm not sure what you're asking. I mean, in principle...
Well, what I'm asking is, usually we're unsure about the coefficients, they're extremely nonlinear.
Exactly.
That's right. You show that basically what you put in, what at least you can get out is very different from what you put in terms of complexity. You can get something more complex out than what you put in, right?
Yep, exactly. And also more general.
Okay. Yeah. But how are we sure that those equations that you
Well, you have to believe me. No, of course, there's no proofs of anything in AI practically. So it's just a matter of testing and testing and testing. I mean, pins and all that stuff that people trust. There's very little rigor. It's just lots and lots of experiments. But hopefully this will come. I mean, once we penetrate what's in these codes, there'll be a priori estimates, which hopefully we can get. But in principle, you can put in some unknown, if you want to do weather prediction or something, God knows what, meteorology, you can input all kinds of equations that are relevant, not too many, let's hope, with parameters, and then input the weather or input the data and try to figure out what the parameters are, and therefore be able to predict more. But that's the goal. So we've done this on a very small scale here, but I think this is very promising because you don't have to many things. You don't have to retrain over and over again. There's no weights. It's just commonalities, and there's an amazing amount of flexibility. You can do inverse problems without sweating it. But proving something is going to take time.
Okay, thank you.
Okay, let's thank once again.
Thank you.